DC Electricity, Part 2, Circuits with Resistance. Section A, Resistors in Series and Parallel. The purpose of a resistor is to limit the current in a circuit, and that enables you to control the heating effects. Resistance is defined to be the voltage across a component divided by the current through it. Advancing physics people also need to know that the conductance is the reciprocal of resistance, that is, it's current through a component divided by the voltage. At A level, you're expected to be able to calculate the total resistance of networks of resistors. However complicated these circuits seem, they all boil down to a set of resistors in series and parallel. Resistors in series provide only one path for the current to flow through, so throughout the circuit the current is the same everywhere, and we can call it I. The supply voltage, or the battery, is equal to the sum of the voltage drops across all the individual resistors, so we can say V total is equal to V1 plus V2 plus V3. And from the definition of resistance, that V total is also equal to I times the total resistance. We can substitute for V1, V2 and V3 using equations that look like V1 equals I times R1, and that gives us an equation that says the total voltage is equal to I times R1 plus I times R2 plus I times R3. We can replace V total with I times R total, and that gives us an equation that looks like I times R total equals I times R1 plus I times R2 plus I times R3. In this equation, the current is the same everywhere, so we can cancel it right out, and that gives us the equation for the total resistance of a set of resistors in series. The total resistance of a set of resistors in series is R1 plus R2 plus R3. If you have more resistors, that equation just carries on adding them in. To find the conductance of a network of resistors in series, we can use the reciprocal relationship to find the conductance of the individual resistors. So R1, which we know is equal to V1 over I, is also equal to 1 over G1. And we can substitute R1, R2, R3 with 1 over G1, 1 over G2 and get R total is equal to 1 over G1 plus 1 over G2 plus 1 over G3. But by definition, R total is equal to 1 divided by G total. So G total, the total conductance of a network of resistors in series, is given by the equation 1 over total conductance is equal to 1 over G1 plus 1 over G2 plus 1 over G3. That's a really awkward expression. I include it because advancing physics says you've got to know it, but I'm not sure why you'd ever use it. Example question. Here is a circuit with 4, 8 and 12 ohm resistors in series. What is the resistance of this circuit? What is its conductance? What current flows around this circuit if the supply voltage is 1.5 volts? First part, what is the resistance of this circuit? We use the equation here, R total equals R1 plus R2 plus R3, and that gives us 4 plus 8 plus 12, and the total resistance here is 24 ohms. What is the conductance? We use the reciprocal relationship here. The total conductance is equal to 1 over the total resistance, giving G total is 1 over 24. The best calculator button to use is the x to the minus 1 button on your calculator, and that gives you G total is 0.0417 Siemens. What current flows around this circuit if the supply voltage is 1.5 volts? We use I equals V over R, so a rearranged version of the definition of resistance, and that gives us I is 1.5 volts over 24 ohms and I is 0.0625 amps. A really useful button to use here is the ENG button, the ENG button on a Casio calculator. This civilises your answer into 62.5 times 10 to the minus 3 amps, or 62.5 milliamps is the easy way to write that one. Resistors in parallel. Parallel circuits provide many routes for the charge to flow along, so more current flows than with a single resistor. The voltage drop is the same across each resistor. The total current flowing is the sum of all the individual currents. You add them up. The rearrangements of the equations for resistance that we've used before apply here, so I total is equal to the voltage over the total resistance, and I1 is equal to the voltage over R1. We can substitute both of these terms into the equation for total current. So this becomes V over the total resistance is equal to V over R1 plus V over R2 plus V over R3. The voltage is the same everywhere here, so it cancels out. The total resistance of a network of resistors in parallel is given by 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Quick example, calculate the total resistance of this circuit. Two resistors in parallel, one is 24 ohms and one is 12 ohms. 1 over R total is equal to 1 over 24 plus 1 over 12. If you're fond of fraction maths, you'll quickly see that 1 over R total is equal to 3 over 24. So R total is 24 over 3. R total is 8 ohms. If you don't like using fractions, you can substitute decimals for those numerical terms on the right. So 1 over R total is equal to 0.0417 plus 0.0833, and that adds up to 1 over R total equals 0.125 and gives us an R total is 8 ohms as before. If you've got a Casio calculator, it's worth experimenting with this button. It enables you to put in two numbers as a fraction. So you can put in one, press this button, it puts a little sort of L-shaped thing on your screen, and then type in 24, and it will give you the decimal. Or you can use brackets, not to work out the fractions, but just work out the final answer. The answer that we got for this problem, 8 ohms, is slightly smaller than 12 ohms, the smallest resistor in the network. That's how we would expect it to be. There's more paths, so more current will flow. We'd expect a lower resistance. It's a good idea to always have that check in your mind, because a really common mistake is that people forget to undo the reciprocal term. So they give me an answer of R equals 0.125 ohms, and this is wrong, and it scores no marks, and that's really sad because you're almost there to the right answer. The conductance of a network of resistors is given by the total current divided by the voltage. In this case, that's I1 plus I2 plus I3 divided by the voltage. Because the denominator is the same everywhere, the total conductance is given by I1 over V plus I2 over V plus I3 over V. Each of those terms is the term for the individual conductance of the resistors, so the total conductance is given by G1 plus G2 plus G3. Exam question. This exam question uses a circuit with a 1.5 volt battery and then a branch called X with two 6 ohm resistors in series in it, and then another branch in parallel to X. This one's called Y, and it's got a 12 ohm, an 8 ohm and a 4 ohm resistor in series, and that whole lot in parallel with X. The exam question says, show that the current flowing through X is 0.125 amp. Explain why the current in branch X is twice that of branch Y, and if point X was connected to point Y by a wire, no current would flow in that wire. Explain why not. The first part, show that the current flowing through X is 0.125 amp. For this one, we know that Rx is two resistors in series, it's 6 plus 6. The resistance in branch X is 12 ohms. The voltage drop is the supply voltage. The current through is given by the supply voltage divided by Rx, so that's 1.5 volts divided by 12, and that gives us 0.125 amps. Next bit, explain why the current in branch X is twice that of branch Y. We know that Rx is 12 ohms, and the resistance of branch Y is 4 plus 8 plus 12 is 24 ohms. Branch X is in parallel with branch Y, so the voltage drop is the same across both sets of resistors. And we can say Ix is V over 12 and Iy is V over 24. So Ix is twice Iy. Final part. If point X was connected to point Y by a wire, no current would flow in that wire. Explain why not. And here's a picture of that situation. In the resistors in series section, we saw that V1 equals I times R1. So for resistors in series, the voltage drop across the resistor is proportional to the resistance. In section X, the two resistors are the same, so the voltage at X is equal to the supply voltage 1.5 volts divided by 2. In branch Y, the two resistors to the right of Y add up to 12 ohms, so again we've got equal sized resistors either side of Y, and the voltage at Y is 1.5 volts over 2, so supply voltage over 2. Vx is equal to Vy, and there's no potential difference between those 2 points, so there's no current flowing. That's the end of this video. If you found it useful, please have a look at part B, which is all about circuits with resistance and current voltage graphs, and then part C is how you use those components and put them in circuits, sensing and control. If you think these videos are good, please subscribe to my YouTube channel. Thank you.